So the same calculations are used for Gibbs energy of formation. You have tables. You can look up their values in those tables. We've used this table for the entropy of reaction, and now we have the other two columns available, the enthalpy of reaction and the Gibbs energy of reaction. And they have thousands upon thousands of these values. You can go to the CRC and look up the thermodynamic properties of compounds, and you can find all of the accepted values for those. But then there's databases that you can pay for that are quite expensive. This one I was going to do for azeotropes and looking at all of the mixing data, and the database and the software that went with it was $13,000. Yeah, it was a huge expense for that research project for the CERDIP. And so, there's some big data tables out there, and there's, you need to write software then to interact with them, because you're not going to go through and flip through thousands of pages to try to find the one line where it's liquid water or gaseous water. So let's do a calculation here. Consider the reaction of oxygen and nitrogen forming nitric oxide. Now, this is an interesting reaction because you could get trapped here. That's not O2. So if you assume that that's 0, you're totally wrong. And if you assume the nitrogen is 0, you're totally wrong. So let's do the delta G of reaction for this one. So you got to make sure you're in the correct column of this table. These are all places where I've seen students go wrong. So you have the product, which is plus 86. And then nitrogen atom can be minus 455 or 456. I'll just round up. And then oxygen atom is minus 230. So can someone calculate that for me, please? Actually, I think I have it right here. 599. Seems a little different. There's a 7.
I think it should be 7.
Yeah, this should be 87 here. Okay, kilojoules per mole. And so that's our delta G of reaction. And so what I want to know is, what is K? So we used this equation earlier. What is K in relationship to delta G of reaction?
Is S? Okay.
We could think, okay, partition functions. We don't want to use that one. It might be easier to see this. Delta G is equal to RT then K.
Yeah.
And so then we move RT over here to the denominator. Actually, it's minus. And so we move RT over to the denominator, the minus sign over there, and so it's E to the minus delta G over RT. And this is negative up here. Okay. And so what we end up with is E to the minus negative 599. And this is kilojoules. We have a choice. Do we want to make the gas constant kilojoules, or we want to make this joules? Because we've got kilojoules and joules. That's a really common mess up.
Make the gas constant.
Okay, so we'll say this is kilojoules per mole, and we'll divide by 0.008314 kilojoules per mole Kelvin. And the temperature, 298 Kelvin. So all of the units cancel. We have a unitless exponent, which is what we want. And I've calculated it. It's e to the positive 241.7.
Jeez. 800.
Yeah. and it may give you an error on your calculator. So if you want to, go ahead and check if you've got your calculator, see if you can type that in and evaluate it. Because I'd like to have a number times 10 to the, I could have a number in scientific notation. Here's one. Okay. Error. Okay. Yeah. So what do we do in this situation? Well, here's a nice little note, a little handy note. When your calculator gives an error on these kinds of calculations, you can just manipulate the logarithms. So we've got an e to the y, and we want to get this in the form of 10 to the x. All right, so we really just want to change the base on this so we can get a number in scientific notation, or at least an estimate. Because, I mean, it's an estimate of e to the 242, but I'd like an estimate in powers of 10, because I just think in powers of 10. So I'd really prefer to have an estimate in powers of 10. So we can do this manipulation. We can solve for x, and it's the ratio of the natural log of 10 to the x over the natural log of 10. But the natural log of 10 to the x, that 10 to the x is e to the y. Well, the natural log of e to the y is y. So we end up with this x, which is what we want to know, is just the exponent in e divided by 2.303. And so this is equal to 10 to the 241.7 divided by 2.303. So it's roughly 10 to the 105. That's a really handy skill.
That's pretty cool.
Yeah, so when you're dealing with something, you end up with an exponential result that's way too big to evaluate with your little machine here. Don't forget, your brain is more powerful than that machine. You may not believe it, but you know algebra. Use it. Okay, have a great day.